Okay, I'd like to ask Dr. Stephen Hare to review this year's stock assessment. And he surprisingly accepted.
Okay, good afternoon, everyone. I have a, usually I don't write down any notes and I just talk to my slides, but I do have a couple of things I wanted to say. I wrote them down just to, I didn't fumble over my words. In my 15 years at the Commission, and I've dealt progressively with bycatch and climate and oceanography, harvest policy and assessment, I can easily say that this is by far the most difficult year to date. As you're all aware, we've been experiencing a steady, decade-long decline in the exploitable biomass of halibut. This year, the staff continued to deal with a number of issues related to bycatch, the effects of migration, changes in size and age, on all facets of halibut management, analyses related to the minimum size limits, among many other things. You'll hear about a number of these analyses tomorrow, perhaps even later today. One thing we can't do, though, is create biomass. Only recruitment and growth can do that, and we've seen precious little of both in recent times. What we can do is practice conservation and ride out this low point in the abundance cycle. And the nagging question that we face here is, with all the cuts we've made for the past 7 years, which were undoubtedly the right thing to do, is have we been adequately conservative, or do we have more work to do? With that, I'll start by walking through some of the changes and updates for 2011, working to the assessment. So each year we get data from a variety of sources that get incorporated from the survey, from our survey, from the commercial sampling programs that we have, data from sport fisheries, personal use, and as well from the bycatch fisheries, the groundfish, trawl, and longline bycatch fisheries. Every year we get some amount of NMFS trawl data depending on which surveys they do. This year there were surveys conducted in the Bering Sea and the Gulf of Alaska. There's not one in the Aleutian Islands. Based on an analysis that we did of the early survey years in Area 2B, we slightly modified the index that we used for various reasons. Some dogfish bank stations were removed from earlier years because they were outside the current area that is surveyed. In fact, we're in shallower waters than our standard survey depth range of 20 to 275 fathoms. Conversely, 2A, we conducted an expanded survey this year, both shallower and deeper, and those are not used in anything other than just seeing what kind of results we got. But there were stations that were filled in the 20 to 275 fathom range, and those were used in the computation of the 2A index. I should mention that those new stations that were not very different from the standard stations we've used in the past. And then finally, we incorporated something I've been meaning to do, which is, we use an adjusted survey index for apportionment purposes. What we've done now is use these adjustments to actually reweight the portions of the regulatory area individual data sets that go into the coastwide data set. So we now match the input data with the combination of adjustments that I'll talk about later for apportionment purposes. So Heather went through the removals here. I just want to highlight a few things here. So I've got a couple slides on some of the data that we get. This is a summary of the recent removals and trends going back to 2004. It's broken down both by area as well as by fishery. The high point in terms of removals in the history of the halibut fishery occurred in 2004. It was just shy of 100 million pounds total removals. And since that point, we have been reducing catch each year. With a big jump taken in 2011, we've got down to 60 million pounds from a high of 100 million pounds. I won't linger on some of these slides. They'll be in this presentation that will be distributed, available online, not too long after the presentation. So these are just for your getting an idea of how variable the reductions in catch, and not always reductions, have been by area. And this is providing a time series back to 1974. And then here's the big picture going back all the way to 1935. We had a period there, obviously from the mid-'80s to the early 2000s, where there was removals were kept at a very sustained, very high level, and we're working our way down from that pretty steeply, and we'll see how much more steep we need to go. But you can see that there's been 6 or 7 straight years of declines. So I just remind folks of this. We surveyed a number of different areas. Area 4 CDE presents a bit of a challenge because we do not, in fact, have a set line survey in that area. It's a very large area with low densities of halibut, and in order to assemble the coastwide data set, of course, I need the Area 4 CDE part, and so it's broken into 5 different areas, and I won't go to the details here, but we use a combination of our set line survey along the 4D edge and Area 4C, as well as an island in 4D. We have NMFS Bering Sea trawl data. We've had in the past ADF and G, North and Sound trawl data, and then last year, although not this year, there was also a trawl survey done in the northern part of the Bering Sea shelf. So those components are all put together, weighted by bottom area to produce various a data set for Area 4 CDE. So I get from each of those 5 different areas a index of density that is apples to apples with our set line survey that's done on the 4D edge as well as in the islands of that area. And so what you have here is our standard unit of density, which is the catch of 0.32 or over 32-inch size halibut per standard skate, which is 100 hooks at 18-foot spacing. And take it back here to 1995, we do some methods to translate survey catches of halibut into the equivalent set line unit. And then those, and I'll get to the dash line here in a minute, the next slide. So these 5 time series then are weighted by the respective bottom area to produce an index for Area 4 CDE, which is the middle bottom panel here. So this is our gold standard, if you will, of the index of exploitable biomass of halibut across the range. I've added this year a dashed vertical line just showing to help folks remember when we transitioned from closed area assessments to the current method of using a coastwide model and data set and then apportionment using the survey. As every year, there's a variety of different trends going on here. We have the measure of WPUE and the associated standard errors in that estimate. And then I have in the bottom right-hand corner an indication of the change from 2010 to 2011. I noted in my opening remarks about this decade-long steady decline in halibut e-bile. That's indicated in the bottom right-hand corner there. The decline this year was less than it was last year, which was on the order of 15%. But it remains a fact that we have not yet arrested this decline in exploitable biomass. There are different signals in different areas, of course. Just draw attention to 2C this year, which I think the cuts were been really the strongest over the past several years. And I don't think that's a coincidence that we saw a 24% increase in 1 year this year. Area 2A also showed a sizable increase over last year, but that you should view with an asterisk that I'll get to in a minute. Area 2B had declined 10% after having seemed to have settled at a little bit higher level, after bottoming out, if you will. And then Area 3A, again, this is, it's 1 year, so don't, you should focus usually on the trend, not just what happened in 1 year, but it is always of interest. But 3A showed for the first time in several years an increase. And then 3B, 4A, 4B, 4CDE, they appear to have leveled out to some extent, but they're not increasing, and this year was a decline. And Area 3B continues to decline more steeply than any other area. This takes those same time series, simply puts them all in one plot, so you can get an idea here of what's happened. For the first time in a very long time, Area 3A did not have the highest survey catch rates. In fact, Area 2C did this year, just edging out Area 3A. And what you should take note of here.
Okay, we got you, Philip. Thanks.
is the variability among areas is considerably smaller than it was earlier in the time period. Part of that is that these surveys were implemented at different times in the exploitation histories of some of these areas. Particularly in Area 4, we were surveying in areas that had been relatively lightly fished, where you would expect to have somewhat higher WPUEs relative to their long-term sustainable level, because there probably was some amount of built-up biomass still residing there. But we've implemented full-on fisheries now in all those areas, and certainly drawn down those western areas to levels that would be more what you would expect in a long-term sustainable level, if we're there or not. You wouldn't expect to see that kind of decline in the areas of, say, 2A through 3A, which have been exploited more or less fully for 60 to 80 years. So that leads me to the next point here. I have two slides here that are a point that I think we need to keep in our minds here as we debate what to do this year. What this plot tries to do is to illustrate the relative decline in removals from each area with the relative decline in the WPUE in each area as measured on our survey. So what I did is I standardized all time series relative to their average over the period of 1997 to 1999, and that's a value of 100. So if you look at each of the plots, the first three dots in all of them should have the line at 100 go right through them, and that's the actual WPUEs and removal levels differ from each area, but this means this way of doing it standardizes them. And so you can look at, if you look at the total coastwide, the bottom right-hand corner, relative to the average survey WPUE from 97 to 99, survey WPUE, which is weight per unit effort, is now 34% of what it was in that period. The removals, however, are still at 60% of what they were in that period of 1997 to 1999. The larger decline in WPUE relative to removals is certainly larger for the areas, particularly out west. And I alluded to part of that explanation has to do with the fact that you're measuring somewhat different periods in their evolution in the eastern areas relative to the western areas, since the western areas may have been, you're measuring unsustainable, relatively lightly fished times relative to the present. So while that looks quite stark, the value of 34% compared to 60%, another means of looking at that is to slide the time series forward. The other thing that was going on in the earlier period, of course, that we were doing closed area assessments, which we believe provided a relatively biased view of the distribution of eBio, and was setting catch levels or harvest rates that may not have been appropriate if the eBio estimates were incorrect. So what I've done with the next one is to do the same kind of data summary, but now the standardization is for the period relative to the 2004 to 2006 time period. So now the 100 line runs through the 3 points from 2004 to 2006. We go to the total panel in the bottom right-hand corner. Then this suggests that relative to where things were when we implemented the coastwide assessment and following the advice that came out of the coastwide model, that we appropriately reduced removals relative to the decline in WPUE. That, of course, begs the bigger question is, if the coastwide target harvest rate was too high during that period, what we've done then is basically maintain that too high target, the coastwide realized harvest rate. The reductions have been appropriate given the reductions in WPUE, but if there was catching up to do, it may not have been done. And of course, the story differs by areas here. One of the big ramifications of moving to the coastwide model was to purposefully set lower quotas in Area 2 because we felt that the target rate had been, the realized harvest rate had been much too high in those areas. And so we were certainly successful in that regard, where we lowered the removals more so than the WPUE had been brought down. This is just something different for your sort of FYI. This is not WPUE. This is the NPUE. This is the number of halibut that are caught in the set line survey. I have here the U30. Oh, I meant to change the colors on here. I didn't. So the lowest line in most of these is the catch of U32, under 32-inch halibut. This is an average number caught per skate. The blue one is the O32 numbers per skate that were caught, and then the line on the top is simply the sum of the two. And so we've seen certainly a decline in the numbers. We've seen in some areas an increase in the number of smaller sized halibut U32s caught, but it's not been a dramatic increase, at least on our survey, to compensate for the full decrease in the number of U32s that we've seen. Okay, that was it for the survey, setline survey data. A couple slides here on commercial WPUE. This is the same sort of thing. We were able to take this back further because we collected relatively standard commercial WPUE data going back to 1974. Prior to 83, it was J-hook data that's indicated by dots, and then it's been C-hook data since then. There's another vertical line there that indicates the transition from open access fishery to either IVQs and 2B or IFQs in areas 2C and westward. And then I've also added that third vertical line just indicating the switch from closed area to coast-wide assessment. And it tells a pretty similar story to the setline survey WPUE, with perhaps not quite as steep a decline in most, which you would anticipate given the ability of the fishery to go after the fish, unlike our survey, which doesn't try to do that. The total panel in the bottom right-hand corner would appear to indicate that there was a 1% increase actually in coast-wide commercial WPUE this year. But that's misleading in that the next to last point there, the 2010 data point, was not at that value when I made this slide last year. At that time, in order to get the assessment done, which I have to present it here at the commission like on November 15th, we have to lock the data set at some point, and I give about 3 weeks then to collect the data. I have to stop it and work with that so I can get the assessment done. At that time, the commercial WPUE data that we had came up to a value of 222. The subsequent value became 210, so a decline of over 5%. It affected the assessment, as I'll show later on as well. So while it appears we increased that 1%, in fact, from the time that the assessment was done last year, the decline in the coast-wide commercial WPUE is on the order of a few percent. Yes, Gary.
Dr. Hare, what's the source, or how do you calculate the error bars on these graphs? It seems to me with the commercial data you would have a discrete number for what's caught and a discrete number for long just to what amount of gear was run. So what's the source of those error bars?
Well, each landing has with them a amount that they caught and what their catch per unit effort was. Right? And so it's highly variable. So there's a mean catch across all of these, but their CPUE varies from person to person. This is reflecting then how variable the different fishers are in their success in catching halibut.
But the total is the discrete point in the middle of the area.
We have samples, of course. We don't get them. We don't get from everybody.
So Steve, on your last point, which was relative to the 2010 number, so the 1% is between 2010 and 2011.
The current estimate for 2010 and the current estimate for 2011, yes.
The current one, but if the 2010 estimate was adjusted down, I guess I don't understand what you said relative to a few percent less instead of 1% more.
If I plotted there the 2010 estimate, it would be above the current point where that dot's located, so that the 2011 would be below the 2010 value.
See, I thought in your description you said that the 2010 had moved down subsequent to the season, but in fact it moved up. So that's. I guess I'm still not getting it.
Okay.
Last year you shut your data set off on November 15th or whatever. You did the assessment. You believed that the number for 2010 was
222.
222, which is not the number that's plotted up there.
That's right. Now it's 210. Now we have the full data set in.
So that 210 is what's plotted.
It is, yes.
So I don't understand. Why isn't 1% the right increase of 1% the right number then?
Well, it is, but it may be that the value that we get for 2011 may drift downwards.
Oh, I understand. Okay, thank you. I understand.
I mean, it may not. In most years, the subsequent decline from the lock-in data set earlier in the thing is only on the order of a much smaller magnitude than occurred this past year. We're not sure why that occurred. We're having to look at that.
I understand. I misunderstood. I thought that this wasn't the right data point, and so when you put the real one in, that would. But
Yeah. I mean, it may turn out that there was a 1% increase, that the value for 2011 won't change.
Sure.
So, as with the Setline Survey, WPUE, there's different stories by areas. 2B has shown quite an upsurge lately in commercial WPUE. When I get to the individual area plots, you'll see that I think a good portion of that has to do with the fact there's been quite a decline in effort in 2B. And that those two are certainly linked, with fewer folks out fishing and being fishing better spots, perhaps. 2C also showed a sizable increase relative to last year. Same thing, just plotting all the time series on a single graph here. 3A remains the highest commercial WPUE relative to the others, and we've seen the same sort of coming together among areas relative to the period in the 90s that we saw for the Setline WPUE as well. This is a new plot here. I just want to give you an indication here. I think this presents a little more clearly what we catch in our survey versus what we estimate to be caught in the commercial catch in terms of age and sex composition. So this is called population pyramid plots. Our survey's on the left. So the red bars indicate catch of females, and the blue bars are catch of males. And you can see the ages here, the age 6 at the bottom, up to age 25 plus at the top. And at the end of each bar is a number, and that's the percent of the total catch that was represented by that sex and age. So the biggest bar in the survey is the 9.3. It's 12-year-old females. They're now the most common catch on our survey, and they represent 9.3% by number of all halibut that we catch on our survey coast-wide. As we've often mentioned in the past, the commercial catch differs quite a bit because of the size limit. It's preferentially targeted on females, and so you see the red bars are considerably larger than the blue bars. It's also the case that in the commercial catch, the most commonly caught fish is a 12-year-old female, which is 15.4% of the total catch. And if you sum across all the female bars, it comes to about 70% of the total commercial catch is female.
So 70% of the commercial catch. What was the survey catch ratio?
I don't know off the top of my head. It's between 55 and 60, I believe.
So clearly the numbers of males, for example, in 2011, those numbers don't add to 100%. So what are the percentages?
Together they add to 100. You have to add both sides.
The females and males
add up to 100.
So you can't tell from this, for example, from your survey, which is more or less a reflection of the population, whether or not there's more males than females, or can we tell that there look like there's more females than males in the population?
There'd still be selectivity involved in that, so that wouldn't be a true representation of the distribution. You need a trawl that caught everything to tell that. So yeah, we can't get it from this. But with the size hooks that we use in our survey, though, there's selectivity involved with that. We will catch, and without a size zone, we do catch more males, but there's still going to be, this is going to be distorted, if you will, by the fact you preferentially catch larger fish, as well as faster growing members of younger ages, as opposed to slower growing members of younger ages. But this is closer to the distribution in the ocean than the commercial distribution, but it's certainly not representative. I mean, I don't think there's any question. There's a lot more males in the ocean than there are females, and the assessment provides an estimate of that, of the relative numbers of both in the ocean.
Are those old males? Like, you've got a big clump there at 25.
Yeah.
So are those above the size limit or under the size limit?
Well, the ones on the right-hand side, obviously, are above the size limit because they're retained in commercial fishery. The survey side, you can't tell. It could be a mix because we catch fish down to 50, 55 centimeters on the survey. So you could have, a number of those could be smaller males that aren't above the commercial size limit.
And why do they turn gray at the top part?
It's a routine I got off the web to do this kind of thing. I didn't know.
I was hoping they were sexually mature or something.
No, there's no meaning to the color marker. There's no meaning to the color gradient.
Gray seems right.
This is percent by numbers.
By numbers.
Pieces.
That's right.
So, I mean, it looks like the commercial catch is about 15% male there by numbers. 15 to 20, 15, maybe between 15 and 20.
It's
But
like
by weight, it would be much
It's like
less.
30% by
Or is
numbers.
it by numbers? And about, so that would be half that or less by weight.
It's not that different. I'm sorry, I don't have the numbers off the top of my head. I can still get that information for you. I do the same thing plotted by weight.
That I was
By weight
thinking,
fraction.
okay.
Are you seeing any changes in the growth rates now, or is they sort of stabilized?
They're still smaller. Another decline. Yeah, they're still a bit smaller. Part of you'd have to look at individual areas and look at subsequent plots. There's a problem with doing. I used to put up average weight, but that's affected by a number of things. It could be incoming recruitment. It could be strong recruitment. So you've got a lot of smaller fish being caught, a decline of bigger ones. There's a number of factors that influence that estimate. What we can look at is the size at age, or the weighted age for different ones, and I can put those plots up. I already have so many plots, I tend not to show that.
But my question is, are we still seeing the decline in size at age?
Yes.
And that decline is continuing, it has not leveled off?
It's less than it was 10 years ago, but they're still declining in size and age. There's a little bit of a recovery.
Varies a bit by area, doesn't it?
Sure, it varies quite a bit by area. And I think Juan looked at some areas in Area 2 where we've seen a bit of a recovery, actually, an increase in size at age amongst the 8 and 9-year-old fish that weren't subject earlier to fishing, whereas their previous ones were. And so there may be some indication of a slight increase in size at age among younger halibut in Area 2 anyway. This is a plot I've been showing, just trying to give you an indication relative among areas, the distribution of the age of females taken in the commercial fishery plotted simultaneously with the maturity curve. So the maturity curve is a solid line, and that's common to all areas. That's the fraction of, for any given age, if you go vertical, that's the fraction of females estimated to contribute to the spawning biomass, the number that are sexually mature. The point at which 50% of the females contribute to the spawning biomass is around 13 to 14 years old, and by age 19 or 20, it's about 100%. So the point of this slide is to indicate what areas are have an increased proportion of their catch on younger females, thereby giving them perhaps fewer opportunities to contribute to the spawning biomass. Curve comparing 4B, which has a large fraction of the distribution shifted to the right of the curve, is quite different than, say, let's pick 2A, where it would be the case that there are not a whole lot of older fish in that area, and so the catch is concentrated on younger fish and perhaps less of an ability to spawn as often, and where this might play a role. We haven't demonstrated this, we don't know that to be a fact, but if there is a local stock recruitment relationship of some sort, you'd want to allow your local residents to have the opportunity to spawn multiple times if their progeny are the ones that actually would return back to their area.
Did you say that maturity curve is the same in each of these plots?
It is. We've done a number of studies sampling the females from different areas and don't find the areas that were checked anyway, haven't found a great deal of difference in the maturity at age from different areas. I mean, principally, we tend to look at 2B and 3A historically, where we have long samples going back, and there's not a lot of variability between those areas anyway. Okay, I'll go through a number of series here about from data we get from the NMFS trawl survey, which I found to be increasingly useful, at least for gauging how the assessment sees things versus how the trawl survey sees things. They provide us with the data each year. This is the Eastern Bering Sea trawl survey is conducted every year since 1982 in the same manner. It's a grid that looks a lot like ours. Ours is at 10 nautical miles, theirs is at 20. And so the point here is just to show where what the catch rates were of halibut in the Eastern Bering Sea this year, and where they caught. The color and the size of the circle conveyed the same information. So the largest catches there along the north side of the Aleutian chain. Here's the same kind of thing. They did a survey in the Gulf of Alaska this year, so I've got it put it in 3 parts corresponding to areas 3B, 3A, and 2C. They have a different method of sampling there. They don't have the standardized grid. The stations change each year. It's ratified random, and they move them around. Sorry.
I like that.
Yeah.
Steve, is this a total mass?
It is. This is everything they catch. It's the density of all halibut sizes that they catch. Later on, I apply a selectivity curve to estimate the E-bio of these. This would be like equivalent to total biomass. And then you apply a selectivity curve, you can estimate what the exploitable biomass is from that. I don't plot it this way. I just do it as sum for the entire area. Here this is the catch in the western Gulf of Alaska. Sorry, this should be eastern Gulf of Alaska. I did switch the header. Rather surprising how little they found in the central Gulf. It was all concentrated on the west side of Area 3A. And they don't appear to trawl too successfully in Area 2C for halibut. There's basically one large dot there. Given the geography of the grounds there, I don't find it too surprising, and don't think that these biomass estimates for 2C are too representative of the actual standing biomass in that area.
Could you go back to the previous one for a second? That is really amazing how little they got in the center.
Yeah, there are quite large error bars in the biomass estimates in 3A, and obviously that's why, because it's much more.
I mean, that's all very trawlable bottoming.
Yeah, and our survey doesn't see that kind of disparity between the western and central part of 3A.
The long lines get lots of fish in there, don't they?
This year they had some different boats involved in this, and I took a couple of days to look closely trying to figure out if there's some vessel effect in here, and there was no smoking gun that I could find. There's no reason to suspect the use of different vessels was an influential factor in this. I would assume Noah looked at that as well.
That's all standardized in the trawl speed and everything?
As far as I know. So so anyway, from those data, then you can compute estimates of both total biomass, which is what those dots portrayed, and then I mentioned the selectivity curve you apply to that, an estimate of exploitable biomass. This slide, so forgot about that. Well, let me talk about that first. So the thing that I've noted in past years as well is the exploitable biomass is a small fraction of the total biomass. You think of how many young halibut there are, how small they are, how many old males there are. They don't reach the commercial size limit. It tends to be on the order of 6 to 7 times as much as the exploitable biomass. So conversely, the exploitable biomass tends to be about 1/6 of what the total biomass is. And that ratio has been shrinking. As you can see, the total biomass has tended to be somewhat level in areas 3B and 3A. The exploitable biomass, however, has been dropping. Now this is a reduction both in the numbers of large fish as well as a sharp decline in the size at age. So those two factors together will combine to produce that effect.
What was the first one?
The
Numbers of?
The numbers of larger halibut, older halibut that have fished out. You'll see when I come to the assessment output, we are fishing now, if you will, in a number of very small year classes relative to what was there before. So there are fewer recruits coming in, and the ones that are coming in are small, or they're small, at any given age, they're smaller than their predecessors. And it's a compounding effect, if you will, to reduce the exploitable biomass. Anyway, the error bars at 3A are quite substantial. I found that a bit surprising, but that previous slide kind of indicates why that is. This is the same thing, just showing numbers instead. We've been mentioning that the assessment shows that there are lots of halibut out there. There are just not a lot of big halibut. You add these numbers here, which are more or less flat, with what you'll see in a minute from the Eastern Bering Sea, which are on the increase, and so you get the idea why there's probably more halibut now than there were 10 to 15 years ago, but there are a lot of small ones, whether they're either young and or small. So I did Eastern Bering Sea is plotted differently, but the green here would be the equivalent of the total biomass. You can see last year was the record high since that survey's been conducted. The exploitable biomass, the total biomass increased about threefold over the past 20 to 30 years. It had a slight decline this year. However, the equivalent of the exploitable biomass. The blue line at the bottom over the long time series is about level, and it's been on a slow, long, steady decline, similar to what we've seen in, from our setline survey. Although the setline survey for 4CDE does leverage this data to provide that number. The point of the inverted triangles there is that that's how I get the index for density, the density index for area 4CDE. We did a 100-station survey across the Bering Sea Flats in 2006, where our average catch of O32 halibut was 16.8 pounds per skate. That value then used as an index varies in lockstep with that blue line, which is what we get as an estimate of the eBio from the trawl survey each year. And so the decline from 12.2 last year to 9.8 this year reflects the 20% drop in the estimate of eBio on the NMFS trawl survey, shown in the blue line there. So one thing we were asked to do this year was to provide measures of uncertainty, or some idea of the uncertainty that goes into the catch number recommendations at the end, things that we both consider or simply highlight, or in some matters don't really incorporate, but it is there though. And so I've tried to provide an illustration here of some of the different types of uncertainty that we have, and it's not unique to us, of course. And then give an indication of the scale of that uncertainty, as well as the nature of it. Does it tend to be sort of around some mean value, or does it have a bias one direction or the other? So the first is comes from our survey. We get a mean value of WPUE or NPUE in our survey each year. What's the next slide? Let me not do that yet. And it's, I mean, there's variation. You look at the CVs around those values in the order of 5 to, it's actually more like 15%. But it tends to be symmetric around those values. But that factors into a lot of steps of the process that we have in there. And there's a bit more of the variability than that. There's an added component that comes from the adjustments that we do to the survey WPUE, and that is trying to correct for catchability differences among areas. We do adjustments both for competition for hooks, as well as when the survey takes place relative to the amount of total removals that come out. So this adds another bit of variability on top of the variability within the survey, and Ray Webster fortunately worked up a little bit of extra. It worked up some of these extra numbers for me just before this, and I can say that whereas the 5 to 15% represents just the variability between stations, if you add in the variability for the adjustment factors, it shifts over to more like 7 to 18 or 20%. So that's anyway. That's one measure of variability in there, and that would translate right into the apportionment that I'll talk about later. Another place that this plays into what I wanted to mention is that these adjustments now are used to weight the input data sets to the assessment, and so each time depending on the apportionment we're going to use, we have to construct a different data set using different weightings, and that has an impact on the output from the assessment of what the estimate of exploitable biomass is coast-wide. And is that on the next slide? No. So I can just talk about it. That for one of the models, for instance, our preferred method ends up with a value of 280, but depending on which of the combinations you use of data weighting, it ranges from 278 to 282 or something, and the other model has a variability of like 258 to 262. So there's an effect of about 3% on the eBio estimates, depending on which of these combinations of adjustments that you use to construct the data set. Relatively minor effect compared to some of the other sources of uncertainty. And I just want to show this because this does be later on. We have our survey from which we get a raw WPUE value, and then we compute the adjustments. And so this plot shows here the raw value is the black squares, and then the factoring in the hook competition and survey timing adjustments gives that red dot, and then we do a common weighting of these when we get to the assessment time frame, to the apportionment stage, and that's the blue line. So that's actually the blue line is what's used for the apportionment, Where this can be influential, I want to note like 2A. 2A I noted this year, its survey WPUE was up like 59%. But last year, back up here, they had a very large effect from both hook adjustment and timing, and so it adjusted upwards their 2010 WPUE quite a bit. If you look at the 2010, the next to last points there, the square up to the circle was a large jump. This year, their adjustment for hook competition and time were quite small, relatively speaking. So they didn't get near the bump upwards that they did. So despite the fact that their survey WPUE increased 59%, the adjusted WPUE was up only a small amount, and it is actually down a bit from the adjusted value for last year. And so I was talking about the weighting input data set. So I put that. Oh, so the other aspect of weighting input data set is this year we went back to considering a different definition of bottom area. In the early days of the coast-wide assessment, we used 0 to 300 fathoms. A few years ago, we switched to 0 to 400 fathoms because there were reports, and we presented some results showing that there is commercial fishing taking place at 0 to 400 fathoms. So it seemed like we should expand our definition of habitat to 0 to 400 fathoms. However, our survey only takes place in 20 to 275 fathoms. So there's certainly a bias in either definition. If you use the density estimates from 20 to 275 fathoms and apply that to the larger area, well, there's going to be a bias because it's not likely that the density in those unsurveyed areas is going to be the same, but we don't have any measure of the density there. On the other hand, if we only use 20 to 275, we're excluding different amounts of bottom area from different areas, and so there would be a bias in that direction. So what I did was to simply do all four combinations of using survey adjustments or not, and using the two different definitions of bottom area, and that's where the e-bio estimates can differ across those ranges of 288 to 292, or 254 to 262, depending on which combination is used. So that's it for the kind of the data. Now to the assessment stuff. So the model now has been fitted to a coast-wide data set. It's been developed, used since 2006. It's quite a flexible model. We have been fitting a number of variants of it to do each year. And one of the most influential components of the model is how you treat survey Q. The model that we went with last year has you treat survey Q as something that we call trendless. In other words, the Q can vary annually, but over the full time of the assessment is to have no trend. So that's reflecting the fact that we try to standardize our survey to the extent possible, and that we're not doing anything to introduce a trend, so we wouldn't a priori expect there to be one, and so the model makes that assumption. Yeah, so Q at the bottom, I have it down what it was asked. Q is, what it really just is a scalar. It's how you go from the numbers you catch in your survey to your estimates of numbers in the population. The catch per unit effort is this value Q times the selectivity, because there's a different selectivity for each age depending on their size, times the estimated numbers. You turn that around, then your estimated numbers in the population are equal to the catch to your catch per effort divided by Q times selectivity. So the bigger selectivity is, the smaller is the estimated number. All other things equal. So selectivity is going up, the estimated numbers will be coming down, and vice versa. So by allowing survey Q to drift, if it drifts upwards, then you're going to get a smaller biomass number than a model where it stayed level over time. The survey Q being constant is what we call the vanilla model. It was used for a few years, where there was no annual variability. Simply, it's fixed every year, and we didn't allow that to vary. One of the ones that's been quite useful, or has been performing well, relatively speaking, is what we call wobble SQ, where survey Q is allowed to drift a little bit over time. We have controls over how much it's allowed to drift, but it's not required to have no trend. If the model wants to give it a trend, it's allowed to get a trend. In some other models, we use varying amounts of commercial data, whether or not we fit to the commercial WPUE, and whether we fit to the commercial catch at age. And then the old model we used here back in the 80s and early 90s, Cajun, which didn't have any survey data in it. So this is the, as you'll see, the model that we opted to go with was this one called Wobble SQ, where survey Q is allowed to drift over time. And these are the estimates that it produces of recruitment and biomass trends from 96 to the present. So the recruitment estimates, you can see it indicates that there are good numbers of age 8 recruits, beginning with about the 98-year class, but those have not really entered the eBio to any great extent yet, given their very slow either growth or size at age, whereas the ones from the 1988 to 97-year classes, which are usually the ones that form the bulk of the fishery, the catch typically is 12 to 18-year-olds in the halibut fishery. Those are quite weak year classes, and those estimates are low. They've stabilized. We pretty much have a good fix on the magnitude of those recruitments, and they do appear to be quite small. The trend in eBio has been steady downward trend. The model has this tendency to estimate an uptick at the end. We'll get to that in a minute. Spawning biomass is estimated to have perhaps bottomed out 4 or 5 years ago and is on a slow increase. And I mentioned the total biomass estimate, which would include all halibut ages 6 and older, all ages 8 and older, including those that aren't susceptible to the commercial fishery, would appear to be that they're higher than they've been at any point in the last 15 years.
So, Steve, can I just ask a couple questions about that for clarity? So it's looking like overall biomass. Do we have records going back further? So we're certainly at a local high, according for total biomass. Is that like the highest in the last 50 years, or do we know that?
Well, this assessment only goes back to 96 because it's a sex-specific model.
Right.
You'll see tomorrow, Juan is working on a longer-term thing as part of the MSE, which is trying to recreate the history, and has developed a method, or is working on a method, to try and estimate back further. So it's tricky because some areas were not fished. You have no idea, for instance, of what the contribution would be from Area 4 CD. It wasn't fished back then. We don't really know necessarily what the biomasses were there. So were things back higher in the early days? Well, unquestionably, if you go back far enough, in the pre-fish days, it was certainly quite a bit higher. Relatively speaking, what it was in the 30s or 40s, I'm not trying to estimate now. I used to estimate these for areas 2B through 3A back to 1935, and I don't recall estimates anymore. We had some idea then when we were trying to figure out like regime effects on recruitment in that, but I have not been running those models of late.
I mean, certainly you've got catch trends. You've shown us go back to the 40s, and
for removals, right?
Yeah, so remove, yeah, and if I think of your earlier plot, we had a pattern of removals that was pretty constant since the, let's say, late 80s through to the mid 2000s. So
early 2000s, yeah.
So so just trying to say, even if we go back to 1980, is this like, do we think we're higher now than we were in 1980? Or can you just can't answer that question?
Well, I would think we reached the bottom in 1973 or 74, and it took a number. I think it was 83 or 84 when the stock was declared rebuilt. In time they were setting catch levels that would be defined to be 75% of surplus production. So by 1980, I'm not sure how high it was, if it was as high or not. I don't have an estimate of that.
Steve, just a question about the variability that the confidence scores seems to be increasing or a lot larger than previously. Is that a function of the model? Or
it is. The models had very few looks at those year classes. So the more recent you are in time, the more uncertain is that estimate.
Okay.
So, once upon a time, the 1995 one was at the front of the thing, and it had quite large. As you get more looks at it, those error bars consistently shrink.
Another question too is just it's looking again like our recruitment pattern. We've had a series of really high recruitments. I know that they're not growing and entering the fishery, but the recruitment pattern, again, you can't go back earlier, I guess, because of the model formulation.
Model.
But it's looking like we've got some of the, at least best year classes that we've had in a long time.
Well, relative to the ones from 88 to 97.
And
It's borne out a little bit by the buildup in the NMFS trawl series. I mean, we see the total biomass there, and the total numbers are certainly adding in the Bering Sea are quite large relative to how far back that goes.
And I see the other thing I note that I don't remember seeing in the past was we're now projecting that the spawning biomass be greater than the exploitable biomass. I don't recall.
They actually passed, I think, 1 or 2 years ago. I mean, they measure very different things. Spawning biomass is a function of age, whereas exploitable biomass is a function of size. So females can contribute to the spawning biomass regardless of their size. Right? So if you're getting in these numbers, these strong year classes, if year classes from this period here, a lot of the females are old enough now to contribute to the spawning biomass, but they're not big enough to contribute to the E-bio.
These are both sexes, though.
Not the spawning biomass. Spawning biomass. I should note that the spawning biomass is just females.
But the total biomass is
It is
males.
both sexes, and the E-bio is both sexes.
I note that the fishery, Steve, the most common age, commercially and in your setline survey, is 12 years old. So that would be that peak at 99, right?
Uh-huh.
This 2011.
Yeah, the 99 year
So,
close.
and the second most common peak is 11 years old. So that's the 2000 bar.
Yeah, these two.
Which are peaks. And
Because they're finally big enough to contribute to the...
right, but those fish are not highly selected, or they'd be less than half of that year class, more than half of the end of the line still. Right?
That's correct.
So as those progress into the fishery, we can expect them to be a major part of the fishery for a few years.
As long as they grow. There's the hope. I mean, we've been banking and hoping on this for a while, but it's very slow in coming. And meanwhile, the older, larger ones are still being fished down, and the smaller, younger ones are not adding a lot of growth or a lot of biomass.
I think the other part of that is the expectation of what the ultimate contribution will be. That given the kind of size of age we're seeing, it's going to be substantially less than, say, the 87, 88.
Yeah.
I have a slide illustrating that point a few ahead.
If you're talking about a 12-year-old female, what would be the selectivity on that cohort?
Off the top of my head, I can't tell you. I'm trying to think.
Less than half?
Oh yes, for sure.
Less than half.
For sure, it's less than half. For males, it's essentially zero.
Females, it's almost nothing. Yeah. But, okay.
So your error bars here are symmetric, I believe, around the point estimate.
They are.
But yet, each year, because of the retrospective pattern we see, and as you pointed out to Rebecca, that the error bars get tighter, but they don't tighten up on the center of those things. They tighten up closer to the bottom of them, I guess. So would we expect, based on retrospective pattern, that, for example, the last year class up there, when we re-estimate it next year, is still going to be in that error bar thing, but almost for sure below the center point?
The way the models works, it'll come down, it'll still be symmetric around that point.
So I guess I'm wondering, historically, over the last several years, whether any of the re-estimated ones have estimated them below the bottom of the error bar that you produced this year. I haven't said that very well. But
No, I understand what you're asking. I don't know. I don't think these come down that much. Some of these have come down, and you'll see them later come down, 7-8% a year. Yes, that certainly is a possibility.
So it's just a question of how much reliance we can put on now the 2000 thing, which looks above the, I guess, dotted line average. Maybe in 5 years it'll turn out it was never above that dotted line because of the retrospective.
The dotted line keeps coming down, too.
And then the dotted line.
Dr. Aaron, still?
Yep.
Yeah, I'm still trying to understand your graph on the list, the 18 recruitment
Okay, that's 2004 year class.
Way on the far right.
Yeah, they're 8 years old at the beginning of 2012, so that's a 2004 year class.
Oh, okay, it'll be 8 years old
At the beginning of the year, yes.
next year.
Well, January 1 or December 31st or at the end of the model run, yes.
Okay. And, what's the average weight of a 8-year-old, or what do they, what age into the commercial?
Well, it differs by sex. It's basically the same question that Gary was asking. Males, a sizable fraction of the males will never recruit into the fishery. I think it's something like the selectivity of the oldest males is on the order of about 0.55 right now, so many of them will never recruit to the fishery. The females begin to recruit to the fishery age, and we start to see them at age, well, some of them at age 8. The largest of the females would be recruiting into the fishery, and we capture them in the commercial fishery by age 8. You know, as each year they get a bit older, a larger fraction is there. The females will fully recruit to the fishery this day and age by the age of about 16 or 17, I believe. We finally reach the full recruitment size, the full recruitment estimate, which is about 120 centimeters. Did that answer your question? So this is trying to convey an idea about the contribution to the exploitable biomass here. Each row here is the estimated contribution to the exploitable biomass by age, going back to 1996. So I've highlighted a few year classes here to show their contribution. The one that we know was really one of the largest, certainly in recent history, not for a very long time, was the 87-year class. And you can see it's quite a bit larger than any of the year classes on either side of it. It was both fairly large in number, and the size at age was very large relative to nowadays. And so, you know, by the ages of 10 to 15 or 16, that was the bulk of the fishery. As it produced each year, you know, it marched along. It was the largest part of the catch there for a number of years in a row. So, you know, the age 12 and 13 right now are the largest here, contributing now to the e-bio, but they don't even begin to compare to how much e-bio was contributed by 12 and 13-year-olds from the 87-year class. And it's unknown how much these will contribute. Eventually, they're dying off, of course, as they're growing and they're being caught. You know, we should expect them to contribute some more because fewer of them have been captured. But they're also growing more slowly, so we don't know to what extent those will grow vertically to reach anything like the 87-year class. And the assessment estimates that there are a number of strong year classes following as well, but they're all growing slowly. So yeah, that's what we're fishing on, and with the hope for future increase is coming from. So just to give some idea of the model fit, which has other issues, but there's, you know, from the traditional means of measuring the fit of a model, this model fits the number of the observations quite well. It shows to the commercial and survey numbers per unit effort from the commercial fishery and our survey, as well as how well it fits the weight per unit effort of halibut. This is looking at how it fits to the numbers caught on the survey. The dots are the catch rates per skate, different ages in each year, and then the yellow line is the predicted numbers that you would catch given the model. Appears to track even oddly moving points fairly well. So we have these same kind of plots for males. I'm just showing a few here to give you an idea. And there's another time. This is fits the commercial catch at age here. This is total numbers of catch that are taken in the commercial fishery, and we predict that as well with the model, and use that as a means of minimizing the fit, finding the best fit. And again, it appears to predict these numbers in the catch very well as well as it does in the survey. So from this perspective, the model seems to be doing a good job. So back to talking about measures of uncertainty for a moment here. We have within any given model that you choose, there's a measure of uncertainty and how you parameterize that model, and it produces an estimate, but there's uncertainty in that estimate, and that's the one we typically convey, and that's illustrated here, looking at the last value of exploitable biomass. We can show this by means of doing a likelihood profile on that on that estimate. And there's two different models here, what we call the trendless and then the wobble SQ. They have different estimates, maximum likelihood estimates of 288 versus 260 million pounds. With the confidence intervals of those range, one is broader than the other, but for the trendless model, it's from 260 to 320. And for wobble SQ, it's from below 200 to just below 350. These are on the order of 20 to 30%. We tend to work with the MLE, and that's what we have done catch recommendations on. But there is this uncertainty, obviously, about that estimate. It's in all these types of models. There's also, just besides that form of uncertainty, there's different parameterizations of your chosen model, as well as alternative models. What I mean by that, I'll try to convey the next two here. There's two things here. So if you set as your base model, then what we call the base 2010, that's a trendless. That's that black circle with both vertical and horizontal bars. Those represent horizontally the 95% confidence interval for the of the E-bio going this way, so it ranges from here to here. And then for the spawning biomass, it would be vertically. So here's the MLE, and here's the 95% cover intervals going here. The other ones with circles and arrow bars are the different major models that I mentioned, different ones that we use that typically do something different about survey Q or add different amounts, use different amounts of survey or commercial catch, and those have produced different MLEs of the two quantities as well as their associated confidence intervals. And you can see there's a range there of 20 to 30% among the different models. But something else that you can do that I did spend a lot of time doing this year in search of the retrospective behavior was to simply take the base model and then switch on or off a bunch of different aspects of that model. So I tried 16 different things in this situation, from trying to estimate natural mortality for both sexes, fixing natural mortality for both sexes, fitting to the bycatch length frequencies, allowing different amounts of drift in commercial Q and survey Q. We have this feature where we can robustify the residuals. We can scale the variance. There's a thing called variance scaling that you can do to deal with process error. There's different weightings on CPUE. That's what the lambda is. How much you allow that to influence the fit. Turning on or off individual or whether or not you have different parameter estimates for the two sexes. We just have a single set for the two sexes. This is allowing selectivity to be domed in the survey as opposed to being asymptotic. Whether or not we fit the total bycatch amounts, and I even tried doubling the amount of bycatch to see what that did. And these are also influential factors, so there's a whole range of uncertainty coming from that as well. You can compare a lot of these using model statistics, and some you can't because there's different weightings involved. As you can see, there's you can, depending on how much you open up things, you can certainly get a range of estimates depending on what choices you make when you're modeling. You do the same. Yeah, Gary.
What's the significance of, say, that number 0.1 after survey Q? What you're allowing that to?
It's just it's something. It's a penalty that you're doing. That it controls how far the survey Q would drift. It's a and then the log of the deviations from mean value in that. So it controls the larger that value, the more it's allowed to drift. So small value means you're tightly controlling how far it can wander. And if you have a large value, you're allowing it to wander a lot further.
So up in the CQ is commercial Q, I guess. So if CQ of 50 is you're allowing that to drift. Great deal.
That's right. That's essentially unconstrained in that case.
Right.
And then you can do the same thing now, taking the other model, the Wobble SQ, as your base model, and doing the same set of 16 different switches on and off to try and see how that affects the biomass estimates. So this slide then is a comparison that we do among the different preferred models, if you will. These are the 6 major ones, the base one from last year, and these 5 alternatives. You have something called residual sum of squares. Then you can compute what's called the AIC, which is the statistical comparison of the fit of each model to the data. And the model that has the lowest value, sort of like golf, its lowest value would be the statistically best fit. And so I set that at 0, just to compare, and the others then are relative to that. Last year, Wobble SQ is also the best fitting model. The trendless was a value of just 2 greater. And the way the AIC units work is anything within a value of 1 to 2 has to be considered a competing model that has a lot of support. When you get to the range of 2 to 4, it's a weak competitor, and anything 4 to 7, it's certainly in the range of 100, simply doesn't fit the data anywhere near as well. So I mentioned why you can get these kind of big ranges of fits. The fit to the data can be very poor. I mean, you can do these things and get the model settled down, produce an estimate, but statistically it doesn't really provide anywhere near as good a fit to the data. And this is the means by which we select among different models.
Right, Steve, refresh my math here. What on the y-axis here, that survey Q and then brackets 10, what's that symbol?
It's 10 to the 6. The actual survey Q is on the order of like 1/6 and that's just a scalar between you catch this many in the survey and there's this many in the population. So if the catch rate is 1, it says, well, there's 6 million of those in the population. It's just
that's just 10 to the 6th.
It's 10 to the 6th power, yeah. Shorthand. So these then are just showing how Survey Q looks estimated each year among these different models. The base, or the one from last year trendless, is this one here, which has a 0 slope over time, and then the others are constrained or held level in different situations. And then these are what are quite influential then in the eBio estimate that you get from there. So the higher the end value here, the lower the biomass estimate is going to be.
The N is the number of data points?
That's how many data that are fit. So we have observation of commercial catch at age, a proportion female. So so the models fit to varying amounts of data. So we're fitting to 3,000 data points and estimating 188 parameters, for instance.
Okay, so K is the number of parameters that are being estimated?
Yes, that's right.
And what's RSS?
Residual sum of squares. It's you're subtracting your observation from your predictions and squaring that.
And what's AIC?
Akaiki's information criterion.
What was the first word?
Akaiki is a researcher who came up with a method of allowing you to do sort of penalized likelihood comparison of different model and how well they fit the data.
Information coefficient.
Criterion.
Criterion.
Okay, I'm just trying to understand the logic here. So, so you're recommending Wobble SQ, where last year you were recommending trendless, and as I recall, the year before that, we've been trendless for quite a few years. So this is the first year. So this is a change in the model parameterization relative to, we've been using trendless for like what, the last three years? And in each of those years, did you also do the Wobble SQ? And the fact is that it's only this year that we're having a difference of that large of the AIC?
Yeah.
I'm just trying to understand a little bit about the history, just trying to...
Yeah, they've always been very similar in their fits. I don't recall more prior to last year how different that they were, but I can look it up. But they were always very, very, very similar, and our philosophy was that we attempt to standardize the survey as much as possible. we have to put some stake in the ground, and so we believe this, and so if we believe our survey is standardized, there should be no reason to expect survey Q to drift or have a trend. Then that's that's why we go with it, particularly if it's very, very close to that fit of the other one. This year, the difference is quite pronounced in their fit, and it's harder to justify that.
20 to me doesn't seem large relative to some of these other jumps here.
But it is, though.
I understand the chi-square criteria, but I also would be interested in just having, let's say, a more intuitive sense of when you're looking at the data fits. You're trying to fit a lot of data. Maybe some of those data are more important than others. You've also done, you've also done some other ways of weighting the data. You said earlier than you had done last year.
That's the input data. That's not the actual data points themselves. Like you construct the numbers per unit effort, for instance, in the thing. So you have to weight them by the bottom area and the survey adjusted. The survey. I'm sorry.
You had said earlier that there was different data weighting that you applied this year than you had used last year.
Right.
Okay. Is some of the difference in the model fit, could some of the difference in the model fit be related to that different weighting of the data?
Well, each of these models is fit to each of the different data sets. This reflects the choice of using the data set that is weighted, that uses 0 to 400 fathoms as the definition of bottom area and applies the hook competition and survey timing adjustment. So that's standard for every model. That's set the same.
Right, but
that's what we used last. That's not what we used last year. Sorry, it's a little bit different. Last year we used 0 to 400 fathoms, but unadjusted for hook competition and survey timing.
But we did use the hook competition survey timing just for the apportionment?
That's right.
Okay. So to what extent then would that change in treatment of the data, like you just said, how would that affect the result from the model? I'm just trying to tease out what's a change in procedure from what's a change because we have one more year data.
Right. Do I have that? I don't think I have that easily accessible here. So we have this for each of the 4 different data sets, if you will, to use. There's really just 4 data sets, depending on whether you use which definition of bottom area and whether or not you apply the survey adjustments. So this is using the preferred method of weighting the data set because the apportionment that we go with, that we recommend, is the 0 to 400 and adjusting the survey. So I use that data set for these model runs. But I have the other ones as well.
Yeah, so I'm not questioning that. I'm just trying to understand whether that could explain, I guess, any of the difference in, let's say, the fit relative to last year.
I don't think so. The data sets vary not very much between the 4 different means of weighting. You see the eBio output at the other end ranges like 1 to 3%. It's very, very minor. I can't fully. I don't recall. The data set that we used last year, like I say, didn't adjust for the hook for the survey and the hook competition. I can certainly investigate whether what the relative difference in the AIC between those 2 models for that data set. I don't have it here with me. I think the Wallace Q still fits quite a bit better for all 4 data sets. That's my sense, my memory, but I don't have the actual stats in front of me.
So on that same kind of question, this is a little difficult to grasp, but why did it get different? Why is trendless so much worse than wobble square this year? And I know you've tried to answer that, and it's hard to point to one reason. But what's the likelihood that wobble square or trendless will be the best next year? Those are issues that also aren't predictable, I don't think. But I don't think we want to get into a mode of having wobble 1 year, trendless the next year, go to NMFS 2, and then vanilla. And maybe that's not likely at all because, as I recall, vanilla is always the worst. But it does raise some questions. I don't know how to explore them.
I guess one of the questions it raises in looking at an assessment is, what's your touchstone for how well you're assessing the bio? And one of the touchstones that's being used here is the delta AIC in terms of what's the best fit to the data.
I mean, it's very hard to pick out the difference. You look at the fits to the different things that I showed. I mean, they all look pretty good. We're talking subtle differences here.
So if they're just subtle, why is 20 so much worse than 0?
That's just the nature of that statistic that anything greater than about 7 just says that.
What's a log function there?
Yeah.
So I'm still trying to understand this too, because if we run this with the current version of, say, last year's data, I mean, because the difference in AIC has got to be, if everything else being equal to what we did last year, the difference has got to be explained by most recent data. Because, if you're using essentially the same kind of, depending on how much the parameters changed, because if you ran the same model last year with data up to last year, and the AIC was identical, essentially, then the difference has got to be, is that still true if we look now at the data up through last year?
It'll put different fits into the data. It's not just that it's fixed into the one change. The fit through all those things is going to change. So there's it's going to fit it differently. It's not just that this year is the only thing that's affected. It's to fit the earlier data differently as well, given this new information.
So, but it's got to be something about the recent data that is leading to that difference?
Well, sure. Adding a year's data influences everything. I mean, it influences how, it's going to try and fit that as well. It adds that into the mix, and you can fit that, and therefore it changes how it fits some earlier piece of data. Because it's a reduction by fitting this one better.
But when we say recent data, it's also additional observations of every previous cohort strength as well. So it isn't just like this year's data.
Right. Well, it's current data of older age classes.
Right. It's new observations for every cohort.
Right. So I saw a decline in numbers of a certain thing, and now it's got a new data point. Well, maybe the decline then, the Z that explains that is a little bit different now. So it's going to trade something off to try and fit that better.
But I think I agree with Jim. It's just if we're going to, it's just a little bit unnerving to be thinking about flipping models from year to year, given that there's a substantial difference in the eBio projections for those two outcomes. So, I mean, I think that's an issue we have to think about how to appropriately deal with, and maybe that's a policy discussion we have to have.
Steve, what would happen if you...
So I'm getting a question from, all right. So, okay, go ahead. Yes, Philip?
On the survey timing and hook adjustment factors, I guess I have a couple, 2-3 questions on that. On alternative 2, wobble SQ, if there was no survey timing or hook adjustment factors in alternative 2, would the exploitable biomass increase or decrease if there was no adjustment?
Well, it's within the range of 258 to 262. I don't remember which of those it is. It would change by very little. And in terms of apportionment, each area would change. Sorry, go ahead.
Yeah, I guess I've never really thought of this before on survey timing, but out here in Bering Sea, the large area and the edge, the spawning takes place on the edge, and the edge is like 100 100 miles from St. Paul and we're 300 miles offshore. So say the edge is like 400 miles from mainland Alaska. And how did the survey timing study factor in possibly fish migrating from the edge towards mainland besides just the commercial fishery timing versus the survey timing? In 400 miles, the fish can move off the edge and then the survey boat goes in there. It has nothing to do with whether the commercial guys are there or not first or the survey boat or after, but whether the fish actually moved off the edge. Was that taken into account?
Not quite
Well, I think it is because we have coverage both on the NMFS trawl survey up on the flats and the set line survey in the other areas. So it's covering that range of where the fish might be.
I'd like to make just a brief announcement. There's coffee back there, but if you put it in the plastic cups, the plastic cup melts. In an effort to avoid taking the last real cup, I put it in the plastic cup and I made a big mess. So if you have to have coffee, you have to get a different cup. Sorry.
So, Steve, a question for you. What?
Okay, so I'd like to follow up on that. You know, I can understand in smaller areas there's fish, the edge is not so far from the fishing grounds, but an area like Bering Sea, 400 miles of fish can in or out. And even if there was a next trawl survey, I guess I just don't know if it's the same as other areas, or if it can be the same factors can be used to measure a smaller area versus a larger area.
You know, Phil, the survey timing adjustment is minuscule in all areas except 2A. I mean, it has. That's not where the action is. The action is in the hook competition adjustment. Survey timing is really, really minor, except in 2A. So I don't know if that puts your mind at ease a little bit, but there's you know, just not much of an effect in anywhere but 2A. So we're also waiting to ask a question. You mind if I take his question while you think that over?
Steve, what happens if you use wobble Q? Go back 10 years and plug everything into it. How does it? Do you get the retrospective analysis? What would the numbers look like for this year?
I'm going to show you the retrospective behavior of trendless and modelless Q coming up. That's what's made my life quite unpleasant.
And every other assessment file.
Can you just remind us what the parameterization of wobble SQ is? Is it, I'm sure you've got it written, or tell me where it's written down. Just the equation of just what does wobble SQ actually mean?
Oh, well, you have an annual estimate of survey Q, and it's controlled how far it's allowed to wander. I mean,
how are you parameterizing the wander is my question.
Right. It's on the log of the.
Is it written? If it's written down somewhere,
It
I can
is,
look it up.
yeah.
Just tell me where to find it.
It's in. Well, we had the big assessment document that Bill Clark and I did. It's in there.
Okay.
In the scientific 83.
Yeah, scientific report 83.
Okay.
Wobble's not the name of some statistician.
It's not. Bill likes to use amusing names for things,
Yeah.
and I saw no reason to.
I appreciate that, but I just all of a sudden I'm realizing, oh, I've always thought it was just a characterization of the way it wiggled around, but maybe it was a famous Norwegian statistician.
Yeah.
Okay. So I'll present results now for those two models, and then I'll get to the retrospective behavior. So one thing we do after you get the model, you decide upon a model, and you go and you plug it into your reference points calculations, and this is the output for base 210, or trendless, it's called. It says that spawning biomass is currently at 43% of unfished, but, and this will come from the retrospective thing, it shows that the earlier S-bio probably dropped below our estimate of B30. For those who don't remember, those horizontal lines, B unfished is the estimate of what the female spawning biomass would be if there were no fishing and the population returned to a natural state. That's how many, that would be the total combined female spawning biomass. Based on simulation work by number of people, then we set as action points B30 and B20, saying that should the spawning biomass drop to a value of B30, we would lower the target harvest rate, and if it dropped to B20, we would stop fishing in theory. At no point in the annual assessments did we ever think we were at B30, but subsequent revision of the estimate of spawning biomass suggests that we were below B30 and presently B43. The right-hand plot takes that same information, transfers it to the x-axis over here, so the 1.0 and 1.5 are respectively B20 and B30. Just mark them vertically, so you want to stay to the right-hand side of the 1.5. The other axis looks at what your realized harvest rate is relative to your target harvest rate. Our target harvest rate is varied between 0.2 and 0.25, and it's a little complicated because now it's at 0.215. It's a little bit different than the 0.2 that was done before. But anyway, we certainly want to be within 0.2 to 0.25, and that mark, according to this assessment, we are. But we, again, you see we drifted into the wrong side of the S-bio line. The same plot for alternative 2, or the wobble SQ. I'm just back and forth. You can see it, things are a little bit different. The B42 is the estimate that we're at here, and this estimates, because it estimates a lower current E-bio of 260 versus 288. You can see there's the base 210 says we're closer to 0.2, but lower E-bio says actually we're up there. So that's that report. This is every year. Then we go and look at, based on the total coastwide E-bio and the estimated distribution of E-bio by the survey, we estimate what were the realized harvest rates in earlier years. And so this is area 2 over here, obviously, area 4. And as we mentioned, a number of years, our estimates now are that there were really, really high harvest rates being visited on area 2 on the exploitable biomass. This was near the end of the days of the closed area assessments. These over here just indicate that the harvest rate measured as E-bio was huge, and it is, but E-bio is a small fraction of total bio, which is what's indicated over here. E-bio is somewhere between a sixth and an eighth, some years maybe even a tenth of total biomass. So this is how you could have harvest rates in excess of 0.6 and still have some fish left, because you weren't catching the ones that are unexploitable. You were only catching ones that were exploitable, and you were measuring harvest rates relative to the catchable ones, not the uncatchable ones. So here comes the big topic. Revision and retrospection. Revision, so this one is asymmetric. Most of the others tend to be symmetric, although the between alternative models tend not to be. We've often had models. If you chose one base model, the other fits would tend to be mostly higher, mostly lower. But revision and retrospection can be big. Retrospection is a big one. I just mentioned revision because I didn't know where else to put it, but that has to do with the fact that the end of 2010 estimate for commercial WPUE was 222. It got revised to 210. That alone caused a revision in the 2010 estimate of 2011 E-bio, on which the quotas were set, to drop from 318 to 292. That same model, now rerun with a new year's worth of data, lowers it 292 to 245. And that's the retrospective change. So this retrospective behavior of the model, it's certainly not new. Halibut's been dealing with it for 20 plus years. It has waxed and waned over time, and it definitely waxed this year. It's not unique to halibut. It's surprisingly widespread. There's been a working group out of the Northeast Lab of NIPS for 20 years, actually called like the Retrospective Working Group. They've been forming a meeting since 1991, and they put out a few reports. They do not even have a diagnostic set of tests you can do to identify the retrospective problem. There's so many potential causes or sources of this retrospective behavior that there's no simple run this test, try that test. They suggest things you can do, and you might get lucky, but there's no common cause to this. It could be a number of things, from model misspecification, the trended parameter, say natural mortality. If you're holding fixed, but it's trending, that could cause it. There's opposite trends in some of your data. You've got one set of data that says one thing, and another set of data that says something else. And, that could cause it. Unspecified mortality. There's a trend in some mortality that you don't know about. It's not there. It's increasing or decreasing. It may be that, and we've had the thing flip in halibut. It used to be that the retrospective pattern changed one way each year. And used to, every time you get there, it'd say, oh, the earlier value was too low, it went higher. And now it's the other way around. And maybe that's there's inertia in the data that as long as things are going down, you're going to have this occur. And it's not until the actual numbers or the biomass reverses that you're going to get that cessation of that behavior. There was a time 3 assessments ago when it seemed to have gone away and it wasn't that big a deal. Now it is a big deal. And I ran hundreds if not thousands of model runs over the month I had to do the assessment here, and did not eliminate it. And continue to work on it. It's troubling, and I'll keep at it. Lots more to do. There's many more. I tended to work with the model this time, but there's data changes you can do, and certainly a lot more model switches. And it's very, very time-consuming. It's a lot of things to keep track of. But and you hear about this, I would assume, tomorrow. This does perhaps suggest lowering of the applied harvest rate to achieve your target harvest rate, since if the eBio is overestimated, then applying the target harvest rate to that is going higher than the intended target harvest rate. Here's what it looks like. So the two models, the trendless on the left and wobble SQ on the right, it shows going last 5 years. So here's the current, this is the one I'm going with actually, here's the current estimated trajectory. Here's this bio, but if you consider 2008, and what you do is you simply take your model, and you don't change anything except peel off 1 year of data. So it's full data set was 2011, subtract 2011, run it, and re-estimate the thing for 2010. And peel off another year of data and run it again another year. So this is the year we thought it was gone. You see this running data flipped around, it didn't seem so bad. It came back. And the way this happens pretty much is by changing its estimate of the relative strength of the year classes. They're smaller numbers at age 8, and then they're going to be lower than each subsequent age in the matrix as you go forward. And we have, it's relatively settled in the earlier ones, but these are the ones that are poised to enter the population right now. And if they come down, it's going to bring these down. One thing that we do hope is you see some shuffling here. These don't have as many views as these here, but there is perhaps an indication of a little bit of a change of behavior there. Yeah, Gene.
So in the upper right-hand panel, you said you had the 2011 is all the data, and you peel off the year's data, and you get 2010. So that's not the trajectory that we had last year?
It's very close to it. It's actually,
but it changed a little bit because you also.
This should be the difference, though, is that they say the commercial.
Because you fit some other things.
Well, this is the model from last year. I didn't do this last year. This year I did for all the different model fits. I'm just examining it to see if it's peculiar to the trendless model. It's certainly not peculiar to the trendless model.
I see, but so I think I get the answer, but I would. It seems slightly different than what you just said. If next year, if you did it with the wobble, and you had 2012, and then you dropped off 2012 and ran over 2011, is it going to be that exact line?
Small differences will occur because of updated data sets. The commercial WPUE dropped from 222 to 210 because state laws came in. They re-aged some stuff. They updated the age a little bit. So there are some relatively minor ones.
Thank you.
The one was that dropped from 318 to 292 was kind of a big deal this year because there was that wasn't just retrospective. That was a revision of data. So it's not exactly the same data as it was done before.
Got it.
So Steve, my take on it is, certainly, at least between those two model variations, the pattern's identical. I'm not seeing any difference between the left and right panels. Is that correct, or am I missing something?
There's slight differences. But this is the same general pattern occurs for all 6 of the models, in fact, as well as some of the, I did where Robin sent me a thing and said, well, what about natural mortality? So I did the run, I tried to see with natural mortality and same thing. So nothing that I've looked at has been able to diagnose this.
Or there's nothing in the sense of one particular model variant is better or worse than another.
That's right. I did it for so I showed the staff here, but yeah, it occurred in all of them. But there's hundreds more stuff I can look at.
Yeah, no, I'm just saying between those two, it looks. I'm not.
Right.
They look essentially
this identical. Would not be a reason to choose between the models.
Yeah.
The question is the retrospective going to continue? I mean, I'd like to think that this is the as bad it's going to get, and it'll go away. I mean, who knows? It may not. But one thing you want to check is how do the current e-bio estimates from the assessment compare to the only other thing that we can compare it to, really, which is places that we have other estimates of e-bio, and there's trawl surveys. So I started assembling these a couple of years ago, and what we found is that in Area 4. They nailed it practically. The estimates of e-bio in Area 4 are very, very similar, which is nice. So the assessment with the survey partitioning is in the red, and then the periodic surveys are their annual surveys, obviously, in Bering Sea, and then they're periodic every 3 years or so out in the Aleutians. 4A, very hard to assemble. I have to take 3 different surveys and add different years. It's a little tricky doing it because you've got the Gulf of Alaska, the Bering Sea, the Aleutian Islands all contributing to Area 4A in different time periods. But given all that, they come together nicely. They're not as close in Area 3. They are closer using model SQ than is the case for the trendless, because you've got a lower estimate of e-bio from model SQ, so you get a closer value. 2C, I don't make any of that again. The survey just doesn't catch the fish there. So, 3A, I'm certain that a big chunk of this is, as you saw in that plot, Gary noticed that the trawl caught no fish in the Central Gulf for whatever reason. So we don't catch a lot of fish in the Central Gulf. And that's one potential explanation. There's others that could have to do with there's no Q correction for the trawl survey, whether or not they miss larger halibut because they swim too fast. This is just taking raw data, Planck's activity curve, and estimating that. So these are the comparisons between those two different data sources.
Are these assessment e-bio lines with the Wobble SQ?
Wobble SQ, yes. And survey partitioning with the adjusted data set. I won't spend lines. I have one of these for each area each year. Just it'll be in the file for folks to look at. What's of interest to these things to me is looking at how things have changed from coast area to coast-wide model. This is the abundance indices panel, where I plot usually the coast-wide assessment. The raw and adjusted survey WPUE. Is there a sense that it's leveling out or turning around? And this plot. And this plots commercial WPUE versus commercial effort. So WPUE is in black and efforts is in purple. So I just kind of page down through these. You can see 2A, the sense of down and maybe perhaps leveling. 2B, you certainly see as we brought removes down, and I mentioned in 2B that the commercial effort has been dropping quite a lot in 2B. With, this is a reflection both of the drop in removals and the decline in effort. And we've seen all sides indicating better times in 2B. I mean, certainly not at this level, but again, that may be not something we see for a while. Area 2C. Also see the decline in effort there, and some turnaround finally in area 2C. These other ones now have the trawl, the NIPS trawl about the error bars, just showing the mean value there. 3A. So basically, change in ages. I have these plots for all areas every year. If you're curious about the response of the ages, you can look at these for each year. It's way too many plots. I'm going to put them on here, but you can track that. There's sort of been a change in these, and they're useful for comparing between areas. So 3A, we're still seeing the WPUE come down here. It did show some flattening out. 3B, we've got kind of the opposite going on in other areas. You've just got still increasing effort in 3B. I mean, it's still sending out more and more effort. And the WPUE, that's the commercial, that serious decline there. And then the bunch of indices are still all trending downwards there. 4A, area 4 had showed some positive, all of area 4 had. We dropped the harvest rate to 15%. We had seen all of the WPUEs tend to stabilize a little bit. And these are the areas where these initial high catch rates simply were never expected to be sustainable. And these were, as I mentioned, relatively lightly fished areas that you would expect that. But we need to find out what is the level at which they would be expected to maintain at a given harvest rate. And it seems we're finding it somewhere around in area 4. It's 4B. This is the first area that we kept the harvest rate, and that was when we saw the quickest bottoming out, if you will, of the declines. But in the last couple of years, we unfortunately fell off of that. We've been trending there for 4 or 5 years, and seen things come back down a little bit. And 4C to E. Onward to apportionment. I'm just about done. So we have lots and lots of numbers. We're not going to show them to you. I have them if you ask for them. We'll show you ones that we think are important. As I mentioned, there's all different ways of weighting the data and the basis for the apportionment. So we try to match how we weight the data set to the apportionment thing that's done. 2 different models. We carried forward all the computations for the last year's, actually the last 3 years model, as well as WPUE. Something that Juan will talk about certainly tomorrow, not today. Alternative harvest rates and what that would mean for catch limits. We were asked to provide some method for, given all this other stuff, all these other uncertainties, we simply still come forward with preferred models or some way to provide a range around those recommended numbers, and we have a pretty ad hoc method, again using the survey WPUE, and I'll explain that in a minute. And then we look at also, given that we don't know which is the right model, if either is correct, but we've got to choose something. Well, and they have different e-bio levels, obviously. So if you set your quotas or your catch levels on one model, but the other was actually the one you should have used, what is the danger of doing so? The harvest rates would be, you thought it was the e-bio was this, so the harvest rate was this number, but if the other model is actually correct, then your harvest rate would be different, obviously. So it could be up or down. If you chose the low model and should have the big one, then your harvest rate you'll get will be lower than what you expect. And then the reverse would occur. If you pick the high, it's actually the low, then you're going to get higher harvest rates than you would want. So, and this is then the other measure of uncertainty that we base the apportionment on the survey relative to survey WPUEs among areas is adjusted for various factors, but there's variability. Let me just remind you here, each of these has a measure of uncertainty around it. We're using, this value, actually we're using this value as adjusted for the competition survey timing. These error bars are reflected in, oops, sorry, I won't go there yet. These values, Ray Webster, our biometrician, had just did some numbers for me showing in reality these error bars, you're going to use the adjusted value, which might be here. Then the error bars around that should also include the additional variability due to competition. And then what it does is it inflates these error bars a little bit. It inflates them by, another 25% above that. So instead of going to here, the 25% it'll put like up to there and down to about here. So it adds a little bit more uncertainty around the apportionment to each area. So as I mentioned, we had the 4 combinations of bottom area and whether or not you use the survey adjustments. We recommend this is what we've used now for 3 years or so. And this is the estimated amount of eBio in each area. So that's 100%, of course. And so these are the apportionment numbers. These are the same now across all models. We selected this one. So it says 2.4% of the biomass for eBios in area 2A, 13.4% in 2B, and so on. So then we should come down here, and that data set appropriate to that apportionment has a value of 288. And so here's what would be the eBio in each area. Now, if you wanted to go with
Just pick up the big button.
hello.
Sorry, it's me again, we lost connection.
Okay, Philip, we're back online.
Anyway, if you go with this combination of weighting adjustment, then this would be the distribution of biomass. So I know these choices of weighting and adjustment have much, much more influence on apportionment than they do on the total biomass value. So, but it was important that we match them. So anyway, so we have all these combinations that are here, and then the same things can be applied to WAPL SQ. And then the final thing that we were asked to do is, so say we choose this model and this weighting, you've got these numbers, can you provide some measure of wiggle room around each of those? And the way that was done was to use the survey CVs, and these are the survey CVs in each area. These are actually not accounting for the variability in the hook competition, survey timing that I just mentioned that Ray had done. So these numbers actually a little bit bigger. That should be like 16%. That should be like 9%. That should be 7.8%. That should be 5.3%, something like that. But they're close. It adds a little more. And then just take that value and go plus or minus that amount to the eBio that you had from this right here. So this is the central value, what I call the next panel. It's the central one. Add plus or 1. The danger of doing this, 2B says, well, we feel, safe, 4A. Say we want to go with plus 1. The problem is if everybody goes with plus 1, well, you add it up, you're no longer at a close to 260. So there would have to be trade-offs, if you will. But, this is one manner of doing it's ad hoc. Well, I am done for now. Talking enough, and I think Bruce is ready to talk. Unless there's something else you guys want to ask me.
Okay. Thank you, Steve.